Hi, this is the fourth video for Math S-323. Last class we introduced matrices. We explored how matrices are representations of linear transformations and what it exactly means for a transformation to be linear. And this close connection to linear transformations is exactly why matrices are so useful in geometry, because rotations, reflections, things of that nature, they are all linear transformations. And though linear transformations themselves are geometrically significant, there are several common types of transformations that constantly come up when you're doing Euclidean geometry in high school. So in this unit, we're going to take a look at how to write down the matrix representations of these types of common transformations. And they're really great because they dovetail very nicely not only with geometry, but also with trigonometry. And there are lots of trigonometric identities that you can actually arrive at sort of through a roundabout way using vectors instead of the old-fashioned way, which was first proven using protractors and straight edges and everything like that. So let's get started. The first thing we're going to talk about are just linear transformations in general as geometry. So a linear transformation is really important geometrically because for Rn, that space, right, that's the set of all the elements of n ordered real numbers. A transformation T carries or maps a line through the origin to another line through the origin, or a plane through the origin to another plane through the origin, if and only if it's linear. T is linear. Remember that an if and only if proof goes in both directions. So if T is linear, it's able to carry a line through the origin to another line through the origin and map a plane through the origin to another plane through the origin, and that implication goes backwards. If T carries a line through the origin to another line through the origin and maps a plane through the origin to another plane through the origin, then it is a linear transformation. Let's take a look at the if part. Exactly how to write this down in terms of notation, my goodness, it's kind of crazy looking. Let's remember our mathematical notation. The first thing here is that we have, this is the if part of this proof. A line can be specified by a point P and a direction vector V. Remember that if you want to identify a line, you normally want a point on the line and slope. That's where point slope formula comes from. But when you're dealing with higher dimensional spaces, slope doesn't really make sense, and instead when you want to get really general, even once you get to three-dimensional space, what you need instead of point and slope is point and direction. So you want some point P, and then you want a direction vector V. Now how does this possibly make a line? Well, let's take a look at this set notation in the second line. This right here. It says this line L equals curly bracket P plus TV, vertical line T, sideways pitchfork R. What does that even mean? Remember that the curly brackets mean the set of elements. And so we now need the recipe for what those set of elements are. The set of elements are the point P plus T times the vector V, where T is any real number. So this line, just as you would expect, are the set of points, because remember when you take a point and you add on a vector, you're going to get another point. So it's the infinite set of points that you get when you take the point P and you add on any scalar multiple of T. So think about that for a minute. That's actually really, really interesting. If you start with small scalar multiples of V, you're going to get, and I'm going to say positive for now, you're going to get all the points that are sort of along here, and then as you make them bigger than 1, you're going to get all the points that go along here. And then when you make them negative, you're also going to get all the points that move along here, because this is the direction that negative V would be in. So this line is saying the set of all points, or the set of elements, which happen to be points, that are formed by taking the point P and adding on any scalar multiple of the vector V. And since we're talking any scalar multiple, a line goes on forever and ever. And since we say any scalar multiple, that means literally any scalar multiple. Really, really high numbers will get us really far away from the point P. Really, really low numbers will do the same in the opposite direction, so that's how we describe a line. Now let's take a look here. If T is a linear transformation, and we have t acting on the line, that means t is acting on the set of all points that are formed p plus t times v, such that t is a member of the real numbers, right? These are all our points in that set. And that equals, because t is linear by linearity, t acting on p plus any scalar multiple of t acting on v. Well, t acting on a point is just going to give us another point, and t acting on v is just going to give us another vector. So what we have here is a point plus any scalar multiple of, granted it's another vector, it's different from v because it's t acting on v, but it's this is just another line, right? We have a point that's been transformed plus any scalar multiple of a vector that's been transformed. And yes, it's a different line, but that's okay. For a plane, the same thing holds. This is how we write a plane in terms of vectors. And note, v and w are two vectors that are linearly independent. They span the plane, which means that if you were, say, considering your piece of paper a plane, and you wrote here's a v and here's a w, that means that all the possible linear combinations, of which there are an infinite number, of v and w, you'd be able to reach any point on your piece of paper, right? If you added scalar multiples of v and w together, you could reach any point on your piece of paper. So what this is saying for a plane, the way to describe a plane in terms of vectors is saying, here's a point on the plane, and then I add on, there's an infinite number of scalar multiples of v and w, which allow us to sort of crawl out along the plane, where t and s, those are the scalar multiples, are members of the real numbers. The same exact thing happens here, where t acting on the plane is t acting on how we describe the plane in terms of points and vectors, which ends up being t acting on p. That's just another point. It's a transformed point now, but plus scalar multiples of t acting on v, which is a transformed vector, plus t acting on w, a scalar multiple of t acting on w, which is another transformed vector. And so this is just another description of a plane. So we have a plane that's transformed into a plane, a line that's transformed into a line, and so this is one direction of that proof. You won't be responsible for that, but it's good to sort of appreciate the fact that we just introduced linearity, and already we can see all of these fantastic properties that make linear transformations so special. Now, for the meat of the matter, let's take a look at isometries. Now, for the purposes of this particular class, we're going to be keeping our discussions of matrices and isometries to the two-dimensional case today, meaning we'll be working in the plane, like our piece of paper is going to be a good physical representation of the plane, and so we're going to be working with 2x2 matrices. So let's take a look. Remember in the last class that when we were given a mystery linear transformation and how it behaves acting on two different vectors, we were able to exploit linearity, figure out how it acts on the standard basis vectors, and exploit the mechanics of matrix multiplication to figure out that, hey, if I know how this transformation behaves when it acts on the first standard basis vector, I know the first column of its matrix representation. And if I know how this transformation acts on the second standard basis vector, I now know the second column of the matrix representation of this linear transformation. So it's really important when we're going through these isometries to not just memorize the formulas for these matrices and memorize the different components of them, but actually be able to reproduce them from scratch. Knowing what these isometries do to the first and second standard basis vectors will allow you to regenerate these matrices from scratch, and you never have to rely on memorization. So first of all, what is an isometry? An isometry is a transformation that preserves the distance between any pair of points, and hence the length of any vector. Very important fact. I think you guys, for those of you who are in groups in symmetry, you've already talked about isometries, and lo and behold, they are appearing here. Let's get started. I put this little side note up here that says, note that if we compute 4 times A dotted with B, we see that dot products can actually be expressed in terms of lengths. Since isometries preserve vector length and dot products can be expressed in terms of said lengths, that means that isometries also preserve dot products. You may be a little suspicious of this particular equality, but try to expand this side. you know that the length squared of a plus b is just a plus b dotted with itself, and the length squared of a minus b is a minus b dotted with itself. And so see if you can simplify down the right-hand side to equal the left-hand side by expanding it first and then canceling out like terms. So let's take a look. Using this result, isometries preserve dot products. The most succinct way to talk about a transformation T as an isometry is saying that a transformation T is an isometry if and only if T acting on A dotted with T acting on B is equal to A dotted with B. Remember that isometries preserve dot products. So that means that when A undergoes this isometric transformation and B undergoes this isometric transformation, taking the dot product between these transformed vectors is not going to change the dot product you get that you compute before the transformation when you take the dot product between the original vectors. All right, let's see here. When writing the matrix associated with an isometry, the first column of T must be a unit vector. Now, why is that? Remember that isometries preserve length, and so the first column is what happens to the first standard basis vector that has length 1. So if we're looking at the transformation of the isometry, that means that the first standard basis vector needs to be mapped into a vector that is also length 1. The second column must also be a unit vector, and its dot product with the first column must be 0, because if E1 and E2, their dot product is 0, then the columns of the matrix representation of the isometry must also be 0, because dot products are preserved. So here are two really common isometries, rotations and reflections. Let's take a look first at the rotation matrix. This is the matrix representation of a rotation through angle theta, where theta is the angle with the x-axis, or the first standard basis vector. Let's break this down instead of just trying to memorize this straight away. We take a look at the first column, and remember the first column is what happens to the first standard basis vector when the isometry acts on it, or the matrix representation of this linear transformation acts on it. Well, let's do a little drawing of the coordinate plane. And here I have E1 and E2 before anything happens to them. Let's rotate both of these through an angle theta. All right, note that theta is this guy right down here. I drew it in both relevant places, and I wrote these new red vectors as TE1, which is what I get after the transformation acts on E1. If we rotate both standard basis vectors, they should maintain the fact that they're orthogonal to each other after the rotation. Let's zoom in on TE1, the effect of the isometry on the first standard basis vector, and break it down into components. Note that if we drop an altitude down from the end of TE1, we now have a right triangle. Its hypotenuse is length 1, which means that the base is cosine theta, from the trig identity and definition of cosine, and its height is sine theta. And so we can see that the components of TE1 are cosine theta is its first component, and sine theta is its second component. And sure enough, we see that in the first column we have cosine theta and sine theta. Let's do the same thing with TE2 and what its components are. We now want to drop an altitude like so. We have the angle theta right here. We have the same sort of right triangle here, but the components are a little bit different. Now we have cosine theta and sine theta on these sides of the triangle. It's the exact same triangle, just sort of tipped on its side. And so we see that the first component for TE2, pardon me, is sine theta, but it's moving in a left direction, so it's negative sine theta. And the second component is cosine theta, still moving up, so positive cosine theta is fine. Sure enough, in the second column, we see negative sine theta and positive cosine theta. Let's do the same thing with a reflection. Now here's our setup for a reflection. When we talk about reflections, we talk about reflecting over a line, and when we're dealing with matrix representations of reflections, we have to be clear about the angle theta that line makes with the positive x-axis. So theta is right here. Now, let's see what happens to E1 when it's reflected over that line. We know that if E1 is reflected over that line, it'll maintain its length, but based on symmetry, this new TE1 will also have an angle theta with the line of reflection. So when we drop an altitude down, just like before, and we create a right triangle, we see that we can quite easily describe the components of TE1 because this base is now cosine 2 theta. Note that this angle here in the right triangle is 2 theta, so the base of this right triangle is cosine 2 theta. The height of this right triangle is sine 2 theta. I'm not going to explicitly label them because our diagram is about to get a little bit crowded. But we can see again that the base is cosine 2 theta, the height is sine 2 theta. And sure enough, that matches to the first column of the matrix representation of this reflection. Now let's see what happens to E2. E2, when reflected, is going to exploit the symmetry in our drawing of exactly what angle it's going to make with this nice turquoise line. We have an angle of theta, we have a mystery angle here, and then on the other side of the line we have an angle of theta, and we need something that's about the same as the mystery angle. And in fact, since dot products are preserved, you know that since E2 and E1 are perpendicular to each other, TE1 and TE2 also need to be perpendicular to each other, so let's go ahead and draw that in. Now, let's label some of these angles that are missing. We already have the fact that we have theta, we have another theta, and now we have a mystery angle, which you might say, how can I possibly know what that is? But note that this entire quadrant has a total number of radians that is pi over 2. So this guy is going to be pi over 2 minus 2 theta. Now on the other side of things, note that we have an angle theta, pi over 2 minus 2 theta. By symmetry, this has to be pi over 2 minus 2 theta as well. And now we are almost home free. We have pi over 2 minus 2 theta. This leaves this angle right here to be 2 theta. So now, when we drop this altitude to the y-axis, we have some nice easy components for TE2. If this angle in here is 2 theta, we know that this side, along here, will be cosine 2 theta in length, and this side will be sine 2 theta. But note that this is downward movement, so we have negative cosine 2 theta in the y component, sine 2 theta in the x component. When we take a look at this, sure enough, the x component has sine 2 theta and the y component is negative cosine 2 theta. And so that's where this reflection matrix comes from. Now let's take a look at composition of these isometries. If we want to apply one linear transformation after the next, that means that we're going to be multiplying by one matrix after the next. And so the composition of isometries is represented by the product of multiple matrices that each represent the isometries we care about. So if we have a composition of isometries which preserve dot products, right, then the composition is also going to preserve dot products. The composition of isometries is another isometry. In a couple of the problems we'll be doing, we're going to try to figure out what the composition of multiple isometries is. And so that means that we need to write down the individual isometries and their matrix transformations and multiply them together. Let's take a look. Remember that order matters. Our first exercise. Show that the composition of two reflections over the same line simply returns a point to where it started. Well, we're going to be using the reflection matrix, and the composition of two reflections means that we want to apply one reflection and then do the exact same reflection again, which means that we'll have reflection 1 and then reflection 2. Remember that since when we have matrices act on vectors, the vector multiplies on the right-hand side of the matrix. That means that order matters here in a way that's a little bit counterintuitive because we're not moving from left to right, we're moving from right to left. The vector is first going to encounter the first reflection and then the second reflection. So what we want to look at are these red terms. What does this total isometry look like? We want to know that the composition of these two reflections returns a point to where it started. And I know that this looks like a vector, but what we're going to be using in general are position vectors, which go from the origin to a particular location in the plane. But we're not caring about the vector at all. What we want to see is, what is this red term? What is this red term? So let's write down F1 and F2. We are preserving order. Note that they are reflections over the same line, so we don't have to change the theta that we're using. Let's multiply them together. Let's take a look. We now want to take this times this plus this times this. So in this position, we have cosine 2 theta times cosine 2 theta plus sine 2 theta times sine 2 theta, which is cosine squared 2 theta plus sine squared 2 theta, and that is equal to 1. Trig identities are a great thing. In this position right here, we have cosine 2 theta times sine 2 theta plus sine 2 theta times negative cosine 2 theta. So we have one term minus itself. So we have 0. Now, let's take a look at this position right here. We have sine 2 theta times cosine 2 theta plus negative cosine 2 theta times sine 2 theta. Again, we have 0 right there. And last but not least, as you might have expected, down in this position we have sine 2 theta times sine 2 theta and minus cosine 2 theta times minus cosine 2 theta. Again, we have sine squared 2 theta plus cosine squared 2 theta. Trig identity, 1. And note that the result of our composition of two reflections is the identity matrix. What happens? What does the identity matrix do? To whatever it acts on, it just returns itself. It changes nothing. And so, yes, this composition of two reflections over the same line returns a point to where it started, because composition of two reflections is just the identity matrix. Our next sample problem is a great one. We want to confirm, both by geometry and by matrix multiplication, that if you reflect a point P first in the line y equals 0, then in the line y equals x, the next effect is to rotate the point counterclockwise through 90 degrees. So we're doing two reflections, and we want to show that their composition, or doing one after the other, will result in a rotation of 90 degrees. So let's write down these two reflection matrices. A reflection in the line y equals 0, well, what is the angle theta that the line y equals 0 makes with the x-axis? That's right, 0. So we want to write down the entire reflection matrix where theta is 0. Take a moment and do that. Here we go. We're left with 1, 0, 0, negative 1. This may seem obvious to you, because another way to think of it is, what happens to the first standard basis vector if it gets reflected in the line y equals 0? It stays exactly the same, so that's why we have 1, 0 here. What happens to 0, 1 if it gets reflected in the line y equals 0? Well, it starts pointing straight down instead of upwards, so we have 0, negative 1. That's another way to reason about it. Well, what happens when we reflect in the line y equals x? What's the angle that the line y equals x makes with the x-axis? Pi over 4 is correct. What does that reflection matrix look like? Take a moment, try to write it down. Here we go. If you're looking at this and saying, hey, I have pi over 4 written down, remember that in a reflection matrix, this term right here is 2 theta. So 2 times pi over 4 is pi over 2. We're left with 0, 1, 1, 0. Is that a surprise? Well, if you take the first standard basis vector and reflect it in the line that makes a 45-degree angle with the x-axis, you're going to end up with the second standard basis vector. And if we take a look at what happens when the second standard basis vector gets reflected in a line of 45 degrees with the x-axis, we're going to end up with the first standard basis vector, which is expressed exactly by this second column. Let's do the composition of these two things. Now remember, the first thing that we want to do is we want to reflect in the line y equals 0, and then we want to reflect in the line y equals x. So we're going to have this matrix on the right and this matrix on the left. All right, we did it, and we're left with this guy right here. 0, negative 1, 1, 0. Huh. Is that the same as rotating a point counterclockwise, a rotation counterclockwise through 90 degrees? Well, let's think about this. If we took the first standard basis vector and rotate it at 90 degrees counterclockwise, we'd end up with the second standard basis vector. So the first column agrees. And how about if we took the second standard basis vector and rotated it 90 degrees counterclockwise, we'd get opposite the first standard basis vector, which that second column agrees. And so that's absolutely true. Now let's show that geometrically. We have a coordinate plane, and we have a line y equals 0. We also have a line y equals x. That only took me 3 tries. Let's start with a point. And of course, we don't have matrices act on points. We have matrices act on vectors. So when I choose this point, which is like 1, 2, basically, down here, I'm sort of looking at, and I actually do the matrix multiplication out in our previous example, I'm having it act on this vector, which is the position vector for that point. But that's okay. We're sort of going to use a loose interpretation of point right now when it comes to the computation, but graphically it's going to make complete sense. The first thing that needs to happen is that point needs to be reflected in the blue line, y equals 0. And so it's going to end up somewhere up here. And then that point needs to be reflected in the green line. And so it's going to end up somewhere right about here. And does this look like a rotation of 90 degrees counterclockwise? Let's take a look. Certainly does to me. Look at that. Very nice. That is like the crookedest line ever, but you guys will forgive me. So not only have we shown this computationally with matrix multiplication, note that I'm going to be really clear with you and say that this is the rotation matrix of R of pi over 2, where theta is pi over 2. And we've shown this geometrically, that it does make sense. Moving right along. Let's look at how matrices can be applied to complex numbers. Usually complex numbers are only very lightly covered in a typical algebra course, but they're an important field, and they just deserve study all their own. And matrices actually lend themselves to a really nice application. Note that the field axioms apply to complex numbers. We notate the set of complex numbers with this scripted C. And the only axiom that's really difficult to check is the existence of a multiplicative inverse for some non-zero complex number. And perhaps just as you may or may not already know, if you have a non-zero complex number, a plus ib, remember that with a complex number there's a real component, a, and then there's a real number that's a coefficient on I, which is the imaginary component, so a plus ib. If you're looking for the multiplicative inverse, you need to take 1 divided by a plus ib. And in order for us to get rid of this imaginary part in the denominator, we need to multiply by the complex conjugate. So we multiply by a minus ib in the numerator and denominator. We're left with a minus ib in the numerator and a squared plus b squared in the denominator. And so our total answer here for the multiplicative inverse of some complex number a plus ib is a over a squared plus b squared minus I times b over a squared plus b squared. Now, we can represent complex numbers as vectors because what's great about when you add two vectors together is that the various components don't interact, right? You take whatever's in the first position and you add it to something else that's in the first position, and then you take what's in the second position and add it to something else that's in the second position in the other vector. Similarly, when you add complex numbers together, the real parts sum together and the imaginary parts sum together, and they really don't mix and match. So when we use matrix representations of complex numbers, we take the real part in the first component and the imaginary part in the second component. And since matrix addition or vector addition keeps those two components separate, it really obeys the laws of adding complex numbers together. Now, let's take a look at the modulus of a complex number. The modulus of a complex number is usually notated like this. It looks a lot like absolute value, but it's actually equal to the square root of the sum of the squares a squared plus b squared. Now, what's particularly interesting is that if you have something that's totally real, like it doesn't have an imaginary part to it, and you just have z equals a plus I times 0, so b is equal to 0 in this particular version. If you wanted to take the modulus of this number, you'd end up with the square root of a squared, which is just equal to the absolute value of a, because the square root can really not be negative in this case because we're looking at the modulus, or absolute value. So for real numbers, the modulus is the absolute value. For imaginary numbers, we sort of refer to it as the modulus more often than not. So the modulus of a complex number ends up being the length of the vector that represents it if we take the real component here and the imaginary component here. So the triangle inequality applies for complex numbers, and this is in fact true. If you take the sum of two complex numbers and take that modulus, it's going to be less than or equal to the sum of the moduli of the various complex numbers. I can't decide if it's moduli or moduluses. Pretty sure it's moduli. Really, this is the basic fact that I'd like you to know, that the modulus of a complex number is equal to the length of the vector that represents it. But there are some other subtleties. For instance, now, since the modulus of a complex number is obtained by multiplying by its complex conjugate, you have to change the dot product because, well, the dot product involves the length of that vector. And so I go into some of the specifics here about exactly what you need to do. But as far as what you'll be doing in class, not going to be applied in many problems at all, but it's some details in case you're interested. While it's very nice that vector addition is a great way to represent complex numbers and add complex numbers together using vector representations, what about multiplication? You can't really multiply vectors together. That's not a thing. So what's interesting is that you can actually also represent complex numbers using matrices, which can be multiplied together. So the geometrical interpretation of multiplication by a complex number is, well, we have z equals a plus ib equals r times e to the I theta, and you might be wondering, what the heck is that? Well, you may or may not have known about the complex plane. The complex plane has the coefficient of the real component of a complex number along the x-axis, the a part, and the coefficient of the imaginary component along the y-axis. That's the b part. So when you're looking at some number that's a plus ib, then its location in the complex plane is going to be a comma b. Perhaps you've studied the polar representation of the plane. When you're looking at polar coordinates, points are not located by their x component and their y component. Rather, when you're looking at an arbitrary point in the plane here, you want to analyze it by its distance from the origin, r, and the angle that a line from the origin to that point makes with the positive x-axis, theta. So the distance from the origin is r, and then you have theta as well. So the conversion there is that x, or in the complex plane, a, equals r cosine theta. And y, or b, in the complex plane equals r sine theta. And so when we say something like a plus ib, if we substitute in these polar identities, we have r cosine theta plus I r sine theta. And if we factor out the r's, we end up with r cosine theta plus I sine theta. And by Euler's formula, that's equal to r times e to the I theta. If you'd like a proof of the fact that cosine theta plus I sine theta is equal to e to the I theta, I am more than willing to do that for you, but I'm going to skip it for now. So that's where this comes from. So when we say z equals a plus ib equals r times e to the I theta, that's just a conversion between various coordinate systems that describe the complex plane. R times e to the I theta is really a multiplication of the modulus by r combined with an addition of theta as the angle. So it's introducing these new measurements, new ways to describe the plane. And really, when we're looking at a matrix representation of a complex number, the way we want to do this is use this. It's a conformal matrix. So we have AB, remember that A is the real component of a complex number, B is the imaginary component of a complex number, and negative B, A over here. That's the same thing if we converted that into a polar description as r cosine theta, r sine theta, and the second column negative r sine theta, r cosine theta. That's a product of this constant matrix where r is the distance from the origin, and then theta over here, this is the rotation matrix. So this is describing distance from the origin, and this is the rotation matrix. It is called a conformal matrix, and it preserves angles, even though it does not preserve length. This is not an isometry. This is something separate. Let's take a look at how useful these matrix representations of complex numbers can be. Our sample problem asks us to write the matrix representation for the complex number 1 plus 2i. We want to multiply it by its complex conjugate to confirm the absolute value of the number is the square root of the product. Because when we multiply something by its complex conjugate, we're going to get the square of its modulus. Now that may have seemed like something totally new to you, but note that all I said was that when we take a complex number and multiply by its complex conjugate, what we have here is a squared plus b squared. And remember that its modulus is the square root of a squared plus b squared. So multiplying by a complex conjugate is going to give you the square of the modulus. Let's see how this works with 1 plus 2i. Now the conformal matrix representation of 1 plus 2i, remember we have the real component here, the coefficient on the imaginary term here, and then we have negative 2 and 1 here. We're going to multiply by the matrix representation for the complex conjugate, which will be 1 and negative 2, positive 2 and 1. So now when we multiply, we have 1 times 1 plus negative 2 times 2, which is 4. So we have 5 up here. 2 times 1 plus negative 2 times 1, we have 0 here. The same thing happens up here, and we're left with 5 down here. And so when we reconvert out of matrix representations into complex numbers, note that this is equal to 5. This represents the number 5. Now, let's check. What's the modulus of 1 plus 2i? Well, that's the square root of 1 squared plus 2 squared, which happens to be the square root of 5. And so sure enough, yes, we get this is the square and of the actual modulus, which happens to be root 5. Here's another sample problem using conformal matrices to represent complex numbers. Use conformal matrices to confirm that the complex number has the property that z to the 5th is equal to 1. Well, let's put this all together. Note that a in this situation is equal to cosine 2 pi over 5. And b is equal to sine 2 pi over 5. All right, let's make that conformal matrix. In the first column, we're going to have cosine 2 pi over 5, because that's our a. In the second position, we'll have sine 2 pi over 5. Then over here, we'll have negative sine 2 pi over 5 and cosine 2 pi over 5. Now, this is an absolute nightmare to have to multiply by itself 5 times, but plug that into Wolfram Alpha if you like, or you can go ahead and do it by hand. Really not too bad because it'll start to simplify almost immediately. And you'll end up with, raising this to the 5th power, you'll end up with 1, 0, 0, 1. And lo and behold, what complex number does that represent? Sorry, that looks like a 6. That should be a 0. That is 1 plus 0 times I, which is just 1. And so sure enough, that means that that number, raised to the 5th power, is equal to 1. Now, we discussed when we first introduced matrices that the matrices do not form a field in general because multiplication is not commutative. If you swap the order, you really may get a different answer. But there are two notable exceptions, and one is 1 by 1 matrices, or more generally n by n matrices that are multiples of the identity matrix, and the other is 2 by 2 conformal matrices. So since multiples of the identity matrix and rotations all commute, the product of two conformal matrices is the same in either order. Another cool fact is that the determinant of a matrix that is conformal is the following, a squared plus b squared, which we know to be the square of the modulus of a complex number. And so the theorem that states that the determinant of a product of two matrices equals the product of their determinants, written out very nicely right here, determinant AB equals determinant A times determinant B, something we will be proving on Monday, means that the modulus of this product is equal to the product of their moduli. Very cool. And that's it for today. You'll be responsible for doing some problems involving isometries and matrix representations of given isometries, as well as some simple representations of complex numbers using matrices and doing some straightforward computations with them.